In the last video we looked at derivation of second order RungeKutta techniques, and we saw that both Hoyne's method and the midpoint method were RungeKutta techniques of the second order. Second order is definitely better than first order, but in practice even second order isn't really accurate enough. And so we want to try and go to higher order solutions. And what we're going to have a look at in this short video is the fourth order RungeKutta technique, which is kind of a very standard high order integration formula for ODEs. So the basic idea of RungeKutta theory that we looked at in the second order video, can be extended to higher order methods. And higher order, of course, usually means more accurate. So the most common is the fourth order RungeKutta method, and it is often abbreviated by RK4, and I will use the expression RK4 to mean a fourth order RungeKutta method. So it involves, again, expanding our desired solution in a Taylor series expansion, keeping terms up to h cubed, keeping terms up to h to the fourth, because there's an h cubed there and there's an h out the front there, and the error in a single step is fifth order, but of course the error in a global integration we can then show is fourth order, so that's why it's an RK4 method. What we seek to do now is to write this term in the braces as a linear combination of terms. So the W's here are weights, so they're numbers, and the K's are derivative estimates, evaluated somewhere inside the interval Ti to Ti plus h. So the OD update, once we have calculated what W1, K1, etc. are equal to, is just a simple update that looks like that. But RK4 is all about how we estimate these things in the curly braces. So as mentioned before, W are the weights and K are the slope estimates. It turns out that the generic fourth order RungeKutta method can be written like this. K1 is equal to the function value at the initial point. K2 is the function value at Ti plus A1h, Yi plus B1K1. K3 is the right hand side, or in other words the slope evaluated at this point. And the K4 is the slope evaluated at this point. So you can see there's an awful lot of constants involved here, and it looks extremely method. So at the moment this is generic. We're going to get a little bit more specific and it becomes a little bit simpler. The mathematics for estimating the weights and exactly where you calculate the K's is pretty intricate, and it's pointless going through that in this unit. It's not important that you know that. It's the same basic idea. You expand the K's in Taylor series, you equate like terms, etc., etc. The 13 constants that we've created here result in 11 equations. So we have an enormously wide choice of how to satisfy this. In fact, we actually have an infinite number of different ways of satisfying these equations. It has been determined that there's various different sets of coefficients that tend to give better schemes, and there is a standard RK4 set of coefficients that gives a scheme that's given by K1 is equal to the function value at the initial point. K2 is the function valuated at a halfway point. So this effectively is like a midpoint method up to here. But then we do K3. So it's like a second midpoint method, except we're now using a second estimate of the slope at the halfway point. And then finally, we use an estimate of the slope at the end point to calculate the K4 term. Then we average these in the following way. We say that Yi plus 1 is equal to Yi plus h on 6 times this set of estimates. Okay, you won't have to remember the RK4 formula, but you will need to understand how to implement it into MATLAB. So, based on the various different coefficients that we mentioned on the previous page, the standard RK4 coefficients are given here. So you can see that many of them are 0. So graphically, let's look at what RK4 is doing. It's a little bit difficult to look at those equations I put up previously and to get any sense out of them. So we're starting at time is equal to Ti, and we're starting at the point yi. That's the information we've got. We make an estimate of the slope, That's K1, that's equal to f of ti yi. We then take a half step. So we go to ti plus half. This sounds like the midpoint method so far. We get to this midpoint and we make an estimate of the slope there. So that's f of ti plus h on 2, yi plus h on 2 times f1. Or, similarly, that could be k1. So we've got the slope there. We go back to the beginning point and we say, let's use the slope that we just figured here and estimate a half step using that slope. So we've gone up to this point here, estimated the slope, gone back to the beginning, done a halfway point to get to this point here. If we were going to use the midpoint method, we would actually go all the way to the end point here, but not in RK4. We then estimate the slope at this point. So that's the third estimate of the slope. We then go back to the beginning and we take a full step size to get to the end point. But we're not actually finished yet. We estimate the slope at the end point. We then average the 4 slopes that we've got, in other words, the slope at this point, this point, this point, and that point, and come up with an estimate of our final solution, which looks like that. So RK4, it's a little bit tricky, but really it's just a slightly more complex version of the midpoint method. There's a few more steps in between. So if you can do the midpoint method, you can do RK4 methods. So it seems like quite a lot of effort. Is it worth it? Well, it appears to be. So if we consider along this axis here the amount of effort we've got to do, and effort here is loosely defined as the number of arithmetic operations we have to take, and if we look at the percent relative error, Euler method has an error that's right up there. Hoynes method, and the midpoint method as well, are significantly lower. There's a third order RungeKutta method that we didn't look at here, we're not going to. The fourth order RungeKutta method is doing much, much better, certainly than Euler method. It scales like about 1. We're around about less than 10 to the minus 5 error for RK4 for the same amount of effort. There's another scheme which we're not going to go into in this unit called the Butcher scheme, which does even better than RK4. So it's a lot of effort, but it's definitely worth it. So the key points regarding higher order methods for the solution of ODEs are the following. The Taylor series method allows higher order solutions, but it has to be done on a case-by-case basis, and consequently no generic coding is possible. You can't write a function, a MATLAB function, that can solve any equation you like. You've got to edit and effectively create a separate solution for each different equation you want to solve. RungeKutta methods use multiple estimates of the slope to improve our accuracy. So RK2 provides a family of methods that includes both the midpoint and Hoynes method. You need to know how to derive RK2 for this course. RK4 is a good higher order method that's very commonly used. You definitely need to know how to be able to code this, or rather learn how to code this, because you will do it in one of your computer labs.